Let's now discuss changing the order of integration for double integrals. Now, we've talked about this when it came to rectangular regions. With rectangular regions, all of the bounds are numbers, okay? All of the bounds are numbers, and we talked about how you could just switch the order of integration here. So if this was dy dx, then you could just switch it dx dy, and you see that these were then switched, and we could do that very easily. We've also discussed an example where switching it wasn't so simple, and in general it's not. Okay, we got to be careful. It's not merely about taking these signs and just switching them. You would get absurdities if you do that, or definitely not what you want. So let's take an example, and we're going to consider this iterated integral there. Now try to integrate that, sine x squared dx, and if you can't think of the antiderivative at the top of your head, don't feel too bad. In fact, the only way to compute that is numerically. But maybe we could do a trick where we switch the order of integration and are able to compute it. So let's try to switch the order of integration of this, okay? To switch the order of integration, we first need to know what the region is. So how do we find the region? So pretend you don't see this for a second and try to figure out how the region will look. Here's how I do it. I look at the second variable. That's y. What does that tell me? It means I'm fixing y as I integrate over x. And so I'll choose a y between the bounds of it from 0 to square root of pi. Throw a y there. And where do I integrate x for that fixed y? I integrate x from x equals y, whatever y I fixed. It's going to be along this line. Here's the function x of y, right? We're thinking about this as a region that's described by functions of y. So from x equals y to the function x equals the square root of pi, and here's that function there, right? Of y, right? So we integrate from here to here, and we do this from 0 to square root of pi. So how does the region look? It looks like this right here, okay? So we move along here from that first integral. You figure out that we got to move along from this line to that line, and the second integral tells you to do that for y equals 0 to y equals square root of pi. And again, that's going to make sine x squared very difficult to compute this way. So let's try to switch the order of integration. So instead of fixing y first, let's try to fix x first. Okay? So we're going to fix x first. That's going to be our second integration. So what we fix first is going to be our second integration. And we're going to integrate y. We're going to integrate y from the function y equals 0 down there to the function y equals x up here. Okay, that would give us the bounds that we need as we integrate over y, and then we go from x equals 0 to the square root of pi to get the that region, the whole region there between 0 and square root of pi. Okay, so how do you switch the order of integration of this guy? Regardless of function, this doesn't have to do with the function. This is the region. Okay, so for any function, this would work. So how do you do this? So how do you switch the order of integration? It looks like this when you switch it. Notice it is not merely moving these two integrals, swapping them. No, you have to pay attention. You have to open your eyes, and you have to think about it. Okay, and so it looks like this. And now let's compute this double integral. So I'm integrating over y. Sine x squared is constant when I'm integrating over y. And so you'll get just y times sine x squared. Now plug in the bounds, 0 and x. So you plug in the bounds into y, because that's the variable we just integrated. You'll get an x. And now this integral, you can compute with respect to x, because you could use u substitution. Use u substitution and compute, and you will get that expression. Plug in your bounds, and you get 1